Werner Heisenberg was a man who reshaped the very foundations of physics and our understanding of the universe. Born in 1901 inches, Germany, Heisenberg was not just a brilliant mind. He was one of the most influential figures in the field of quantum mechanics. His work, particularly the uncertainty principle, would change the course of modern physics forever. However, to truly appreciate the significance of Heisenberg's contributions, we must delve deeper into his life, the environment in which he worked, and the monumental challenges he faced. Heisenberg's early education was steeped in the rigorous traditions of classical physics, a field that had dominated science for centuries. Classical physics, based on the laws set forth by Isaac Newton, assumed that the universe operated in a predictable, deterministic manner. In this framework, the position and momentum of an object could be measured and calculated precisely. There was no room for uncertainty or randomness in the classical world. But as Heisenberg advanced in his studies, he began to question the assumptions of classical physics. In the early 1920s, Heisenberg entered the world of quantum mechanics, which was itself a radical departure from classical thinking. Quantum mechanics, founded by pioneers like Max Planck and Albert Einstein, was a new theory that sought to explain the behavior of particles at the smallest scales of nature. In this strange and unfamiliar world, particles did not behave in predictable ways, and their properties such as position and momentum were not as clearly defined as in classical mechanics. Heisenberg found himself drawn to this new frontier, studying under the guidance of the legendary physicist Niels Bohr in Copenhagen. Bohr's work on atomic theory was groundbreaking, and Heisenberg was one of his brightest students. It was under Bohr's mentorship that Heisenberg began to push the boundaries of classical thinking. As he studied the nature of light and atoms, he found that the classical ideas of precise measurements were simply incompatible with the behavior of subatomic particles. One of Heisenberg's key realizations came while he was working on the mathematical formulations of quantum mechanics. He noticed that when scientists tried to measure certain properties of particles, such as their position and momentum, there were fundamental limits to the accuracy of these measurements. The more precisely one tried to measure the position of a particle, the less precisely its momentum could be determined, and vice versa. This was a profound realization. It suggested that at the quantum level, the universe didn't operate according to the deterministic rules of classical physics. Instead, it was governed by inherent uncertainty. This discovery was revolutionary. It wasn't just a new finding in quantum mechanics. It was a challenge to the very core of how scientists had viewed the universe. Heisenberg had uncovered something deeper. The very act of measurement itself seemed to alter the properties of the system being measured. This was not a flaw in measurement techniques, but a fundamental characteristic of nature. As Heisenberg put it, it was impossible to measure certain pairs of properties of a particle with perfect accuracy simultaneously. This was the essence of the uncertainty principle. Heisenberg's uncertainty principle was formalized in 1927 in what would become one of the most famous equations in the history of physics. The equation expressed the relationship between the uncertainties in the measurements of position and momentum. Simply put, it stated that the product of these uncertainties could not be smaller than a constant value. This meant that at the quantum level, there was a limit to how much information could be known about a particle at any given time. The more precisely we measured one property, the less precise our knowledge of the other would be. At first, Heisenberg's uncertainty principle was met with skepticism. It was a shocking concept for many scientists, especially those who were steeped in the deterministic traditions of classical physics. The idea that nature itself could be uncertain was difficult to grasp. But over time, as more experiments were conducted and the strange behaviors of subatomic particles were observed, Heisenberg's theory gained acceptance. The uncertainty principle became one of the cornerstones of quantum mechanics, and it helped to shape our modern understanding of the microscopic world. One of the key aspects of Heisenberg's discovery was its implications for the nature of reality itself. Before the advent of quantum mechanics, scientists believed that the universe was a mechanical system, like a giant clock, with each part interacting in predictable ways. If we knew the initial conditions of a system, we could predict its future behavior with absolute certainty. But Heisenberg's uncertainty principle suggested that the universe at its most fundamental level was not predictable in this way. Instead of a deterministic reality, quantum mechanics proposed a probabilistic world, where the exact state of a system could never be fully known. This was a seismic shift in the way scientists thought about the nature of the universe. It meant that, at the smallest scales, the universe could not be fully understood by classical physics. Instead, quantum mechanics introduced the concept of probability and uncertainty as fundamental aspects of reality. The idea that we could never know everything about a system simultaneously challenged long-held philosophical assumptions about the nature of knowledge itself. It forced us to rethink what it meant to know something and what it meant to understand the world around us. Heisenberg's work went far beyond just the formulation of the uncertainty principle. He was a key player in the development of quantum mechanics as a whole. His matrix mechanics, one of the first formulations of quantum mechanics, laid the foundation for much of the theory. Alongside other pioneers like Niels Bohr, Max Born, and Erwin Schrödinger, Heisenberg helped to create a new framework for understanding the behavior of particles on the quantum level. The implications of this new theory were profound, leading to advances in technology that continue to shape our world today. The uncertainty principle also had philosophical implications that went beyond the realm of physics. It raised questions about the limits of human knowledge and the nature of reality itself. If the universe was inherently uncertain at the most fundamental level, then how could we ever truly understand it? Heisenberg's work challenged not just the physical sciences but also the philosophical foundations of knowledge. In a sense, Heisenberg's discovery was not just a scientific breakthrough, it was also a philosophical revelation. Heisenberg's contributions to physics were not limited to the uncertainty principle. He was instrumental in the development of quantum mechanics, nuclear physics, and even the study of the atomic bomb during World War II. His influence extended far beyond his scientific discoveries, and he became one of the most respected physicists of his time. In 1932, Heisenberg was awarded the Nobel Prize in Physics for his work on quantum mechanics. Despite the challenges he faced, including the political turmoil of Nazi Germany, Heisenberg remained committed to advancing the field of physics. As we reflect on Heisenberg's life and work, it's clear that his contributions to science went far beyond just one principle or one equation. His discovery of the uncertainty principle changed the course of physics and opened up new ways of thinking about the universe. But more than that, Heisenberg's work challenged us to question our assumptions about reality itself. He forced us to confront the limits of our knowledge and embrace the uncertainty that lies at the heart of the quantum world. Heisenberg's journey was not just one of scientific discovery, it was also a journey of intellectual courage. In a time when classical physics reigned supreme, Heisenberg stood at the edge of the unknown, daring to ask questions that others feared to ask. His willingness to explore the strange and unfamiliar world of quantum mechanics, even when it defied all traditional understanding, marked him as one of the true pioneers of modern science. And in doing so, Heisenberg helped to lay the foundation for the incredible advancements that have shaped our world today. In conclusion, Werner Heisenberg's discovery of the uncertainty principle was a turning point in the history of science. It forced us to rethink the very nature of reality, to embrace the idea that uncertainty is a fundamental aspect of the universe. Heisenberg's work opened the door to the strange and fascinating world of quantum mechanics, a field that continues to shape our understanding of the universe. But perhaps most importantly, Heisenberg's legacy reminds us that science is not just about finding answers, it's about asking the right questions and being open to the possibility that the answers may be far stranger and more profound than we ever imagined. As we continue to explore the profound impact of Werner Heisenberg's uncertainty principle, we delve deeper into the intricacies of the principle itself and its far-reaching consequences on both physics and philosophy. Heisenberg's discovery not only changed the landscape of quantum mechanics but also altered our understanding of the universe at a fundamental level. The uncertainty principle asserts that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. This idea was initially difficult for many scientists to accept. It stood in stark contrast to the deterministic worldview that had been the foundation of classical physics for centuries. In classical mechanics, as set out by Newton, it was assumed that, if we knew the position and velocity of an object at any given time, we could predict its future position and velocity with perfect accuracy. Heisenberg's uncertainty principle, however, shattered this belief by asserting that this kind of precise prediction was impossible at the quantum level. To understand why this was so radical, it's essential to consider the context of Heisenberg's time. Classical physics was based on the idea that the universe operated like a clockwork machine, with every particle's position and momentum determinable at any moment. The success of Newtonian mechanics in describing the motions of planets and everyday objects had given rise to the belief that the universe was ultimately knowable. But quantum mechanics, the new theory that sought to describe the behavior of particles at the smallest scales, revealed that the universe, at its most fundamental level, was unpredictable. Heisenberg's work in the early 1920s was rooted in the emerging field of quantum theory. One of the main goals of quantum mechanics was to understand the behavior of atoms and subatomic particles, objects that could not be described by the laws of classical physics. Heisenberg began to see that, as scientists delved deeper into this world of tiny particles, they were faced with a paradox. On one hand, the act of measurement was supposed to reveal the properties of a particle. On the other hand, the act of measuring the particle's position seemed to disturb its momentum, and vice versa. In other words, it was as if the act of observation itself influenced the very thing being observed. This realization led Heisenberg to formulate the uncertainty principle, which became one of the cornerstones of quantum mechanics. The principle states that the more precisely we measure one property of a particle, say, its position, the less precisely we can know another property, such as its momentum. This relationship is not a limitation of our instruments or a fault in our ability to measure. It is a fundamental characteristic of nature. The equation that expresses this uncertainty is known as the Heisenberg Uncertainty relation, dx dtp chanta h4p, where deltax is the uncertainty in position, deltap is the uncertainty in momentum, and h is Planck's constant. This equation shows that the product of the uncertainties in position and momentum is always greater than or equal to a fixed value. The smaller the uncertainty in one property, the larger the uncertainty in the other. This principle was revolutionary because it suggested that there was a fundamental limit to how much we could know about a particle at any given time. It meant that the universe, at the quantum level, was inherently unpredictable. Classical physics, which had dominated our understanding of the universe for centuries, assumed that the world was deterministic. If we had enough information about a system, we could predict its future behavior with perfect accuracy. But Heisenberg's uncertainty principle showed that, at the quantum level, nature operates according to probability, not certainty. The implications of this discovery were far-reaching. It meant that the concept of a precise measurement was no longer meaningful in the quantum world. A particle's position and momentum were not fixed in the way we had once believed. Instead, they existed in a state of probability, and our measurements could only give us a snapshot of that probability. This idea of uncertainty in quantum mechanics was a sharp departure from the certainty of classical mechanics. One of the most important consequences of the uncertainty principle was the way it reshaped the understanding of quantum systems. In classical physics, the behavior of objects was predictable, and the world was seen as a well-oiled machine operating according to immutable laws. But in the quantum world, things were different. The uncertainty principle introduced a new way of thinking about reality. Rather than seeing particles as discrete objects with definite properties, scientists began to view them as existing in a state of probability where their exact position and momentum could not be known simultaneously. This shift in thinking had profound implications for the field of quantum mechanics and, eventually, for the development of quantum technologies. The uncertainty principle provided a framework for understanding phenomena like wave-particle duality and quantum entanglement, both of which would become central features of the theory. The principle also played a key role in the development of quantum field theory, which is now the standard model of particle physics. While the uncertainty principle was initially met with skepticism, it gradually gained acceptance as experiments began to confirm its predictions. In fact, the principle became one of the cornerstones of quantum mechanics, shaping the way physicists think about the behavior of particles at the subatomic level. The experimental confirmation of the uncertainty principle came in a variety of ways, from the behavior of electrons in magnetic fields to the diffraction patterns of light. Each of these experiments showed that particles did not behave in the way that classical physics had predicted. Instead, they exhibited behavior consistent with Heisenberg's uncertainty principle, reinforcing the idea that the quantum world was fundamentally different from the classical one. Beyond its impact on quantum mechanics, the uncertainty principle also sparked a wider philosophical debate about the nature of reality. In the deterministic worldview of classical physics, the universe was a machine that could, in theory, be understood and predicted with enough information. But Heisenberg's principle suggested that there were limits to human knowledge. If we could never know everything about a system, what did it mean to know something? What was the nature of reality if we could not measure it with perfect precision? Heisenberg's uncertainty principle also raised questions about the role of the observer in quantum mechanics. In classical physics, the observer was considered separate from the system being studied. But in quantum mechanics, the act of measurement itself played an active role in determining the properties of the system. This idea led to the famous observer effect, which suggests that the very act of observing a quantum system can influence its behavior. This was a radical departure from classical ideas and further reinforced the notion that the quantum world was fundamentally different from the macroscopic world we experience. As Heisenberg's uncertainty principle gained acceptance in the scientific community, it began to inspire new ways of thinking about both physics and the universe. It led to the development of new technologies, including lasers, semiconductors, and quantum computers, all of which rely on the principles of quantum mechanics. These technologies, many of which we now take for granted, would have been unimaginable without Heisenberg's groundbreaking work. The uncertainty principle also became a powerful metaphor for uncertainty in life itself. In a world where we can never fully predict the future or know all the details of a situation, Heisenberg's discovery reminds us of the limits of our knowledge. It tells us that uncertainty is not something to fear, but something to embrace. Just as quantum particles exist in a state of probability, so too do our lives unfold in ways that are often uncertain and unpredictable. In conclusion, Heisenberg's uncertainty principle fundamentally transformed our understanding of the universe. It challenged the deterministic worldview of classical physics and introduced a new, probabilistic framework for understanding the behavior of particles at the quantum level. Heisenberg's discovery has had a profound impact on physics, philosophy, and technology, and it continues to shape our understanding of the microscopic world. It was a groundbreaking moment in the history of science, one that pushed the boundaries of human knowledge and opened up new frontiers in our quest to understand the universe. The legacy of the uncertainty principle lives on today, influencing everything from the development of quantum technologies to our understanding of the fundamental nature of reality. The deeper one travels into the microscopic world, the stranger the universe becomes. It was here, in this hidden landscape of electrons, photons, and atoms, that the foundations of human certainty began to crack. The classical world, the world of falling apples, orbiting planets, and predictable machines, seemed solid and dependable. Everything had its place, every motion had its cause, and every cause had its measurable effect. But when scientists started examining nature at a smaller scale, the rules began to warp, twist, and ultimately collapse. In this fragile new territory, Werner Heisenberg uncovered something that would change physics forever: the core idea that there is a fundamental limit to what can be known. Not because our tools are weak, not because our eyes are imperfect, but because the universe itself is built upon an unavoidable, unbreakable uncertainty. Imagine trying to study an electron. In the classical world, this shouldn't be difficult. You'd simply observe where it is, how fast it's moving, and chart its behavior. But the electron refuses to play by these ancient rules. The moment you try to observe it, the moment you attempt to shine light upon it, capture it, or pin down its motion, it shifts, jumps, blurs, or disappears entirely from the place you expect it to be. The more you try to confine it, the more it slips through your intellectual fingers. Heisenberg realized that this was not an accident of laboratory technique. It was not the fault of the microscopes or the weakness of human instruments. It was something far deeper, a property of reality. In the heart of this mystery lies the true core of the uncertainty principle, the realization that nature at the quantum level has built-in limits to measurement. Heisenberg saw that there are pairs of physical properties that cannot be known with perfect precision at the same time: position and momentum, energy and time, angular momentum, and angle. Each pair is locked in an eternal dance of limitation. You may know one partner well, but the clearer that partner becomes, the more the other dissolves into uncertainty. It was a revelation that punctured the classical belief that the universe was a perfect watch, every gear measurable, every tick predictable. To explain this behavior, Heisenberg visualized the process of attempting to observe an electron. Light, which is itself made of photons, must strike the particle to reveal its location. But those photons, even in their gentlest form, interact with the electron. They nudge it, disturb it, shift its momentum. Observing the electron's position becomes an act of influencing its momentum. And on the other hand, if one wants to measure momentum, one must use longer wavelengths of light that disturb the electron less but make its position blurrier. The universe forces a choice. If you choose to focus the spotlight more precisely on one property, the other one fades. If you widen the spotlight to capture the other, the first slips away. This was not a philosophical argument, it was embedded in the mathematics of quantum mechanics. When Heisenberg derived the equations that governed electron behavior, he uncovered something astonishing. The uncertainties were not accidental, they were unavoidable. They were not nuisances to be eliminated with better instruments or improved microscopes. They were woven into the fabric of nature. The more precisely you know deltax, the uncertainty in position, the larger deltap, the uncertainty in momentum, must become. Their product could never be smaller than a specific constant value derived from Planck's constant. The universe had set a cosmic boundary. This limit was not up for negotiation. It was the mathematical architecture of quantum reality. This realization shattered centuries of scientific assumption. Classical physicists believed that if you had enough information, if you could measure precisely enough, you could predict the future exactly. The universe seemed to obey strict laws of cause and effect. Pierre-Simon Laplace famously imagined a superintelligence that, armed with perfect knowledge of every particle's position and momentum, could predict the entire future of the universe and reconstruct its entire past. Heisenberg destroyed this dream. The universe, he showed, does not provide perfect information, it prohibits it. The quantum world is not a realm of absolute knowing. It is a realm of probability. This was not merely a scientific shift. It was a philosophical earthquake. It suggested that the universe was not deterministic at its core. It suggested that there was no hidden script that physics could read to tell the future. Instead of certainty, there were probabilities. Instead of precise trajectories, there were waves of possibilities. Instead of solid electrons spinning like planets around a sun, there were clouds of potential positions, each one collapsing into reality only when observed. The core idea of the uncertainty principle also revealed why electrons orbit atoms in the strange way they do. If an electron's position and momentum could both be known precisely, it would collapse into the nucleus, spiraling inward under the attraction of positive charge. But the uncertainty principle prevents this collapse. The electron cannot have both a precise position and a precise momentum. Its natural state is a balance between the two uncertainties. This is why atoms do not implode. Uncertainty is not a flaw, it's the structure that allows matter to exist. Heisenberg's insight also explained why electrons form orbitals, regions of space, where they are likely to be found. These orbitals were not physical shells, but probability patterns created by the mathematics of uncertainty. The atom, once imagined as a miniature solar system, became far more complex, more beautiful, and more mysterious. At its heart was a dance between what could be known and what must remain uncertain. This idea, simple yet profound, forced physics to abandon the comfort of determinism and embrace a universe where chance and probability ruled the smallest domains. As scientists began to accept Heisenberg's insight, quantum mechanics blossomed. Schrödinger's wave equation, Born's interpretation of probability, Dirac's relativistic quantum theory, all were built atop the foundation Heisenberg laid. Quantum mechanics was no longer a collection of strange results. It had become a coherent and deeply mathematical framework. It was a new language for describing nature, one that acknowledged the limits of knowledge not as weaknesses but as truths. Heisenberg's core idea became a guiding principle. The universe is not fully knowable in the classical sense, but it is deeply structured, and its structure includes uncertainty as an essential feature. In the laboratories of the 20th century, researchers tested the principle again and again. Every experiment confirmed what Heisenberg had predicted. Electrons behaved like waves when unobserved and particles when measured, an unpredictable duality governed by uncertainty. Photons exhibited interference patterns, disappearing and reappearing in ways that defied classical instinct, but were perfectly consistent with Heisenberg's equations. The uncertainty principle, once a bold claim, became a cornerstone of modern physics. The principle also revealed something profound about nature. Measurement is not passive. To observe the universe is to interact with it. To measure is to disturb. This meant that nature itself resists being pinned down. The quantum world is constantly in flux, its properties floating in a sea of probabilities, never fully settling until forced to do so. This behavior is not a flaw. It is the very essence of physical law. Heisenberg's core idea became a guiding light in the development of quantum technologies. Lasers, semiconductors, atomic clocks, quantum cryptography, and emerging quantum computers all rely on the delicate, precise manipulation of uncertainty. What began as a philosophical challenge to classical thought evolved into the backbone of modern technological advancement. Uncertainty was not merely tolerated, it was harnessed. Yet the core idea of the uncertainty principle also carries a strange kind of beauty. It tells us that even the smallest pieces of the universe are unpredictable. It tells us that the cosmos is not a stagnant machine but a living tapestry of possibilities. It tells us that knowledge has boundaries, not because we are weak, but because nature is profound. In the end, Heisenberg's uncertainty principle is not simply a rule about measurements. It is a revelation about the nature of existence. It shows that uncertainty is not chaos but structure, not ignorance but the universe's deepest wisdom. The relationship between the position and momentum of particles is one of the most fundamental concepts in physics, especially in the realm of quantum mechanics. In classical physics, position and momentum were seen as properties of an object that could be measured independently and with great precision. These properties followed deterministic rules, meaning that if we knew the position and momentum of an object at one point in time, we could predict its future behavior. This deterministic view was the backbone of classical mechanics and allowed scientists to predict the motion of planets, the behavior of everyday objects, and the results of physical interactions. However, in the quantum world, this simple picture begins to break down, and the uncertainty in the relationship between position and momentum becomes a central feature of the quantum landscape. Heisenberg's uncertainty principle fundamentally challenged the classical view by stating that it is impossible to measure the position and momentum of a particle with perfect precision at the same time. The more accurately we try to measure one of these properties, the less accurately we can know the other. This is not due to limitations in our measurement tools, but rather a characteristic of the quantum world itself. This realization was one of the key insights that led to the development of quantum mechanics, a theory that governs the behavior of particles at the smallest scales of nature. Heisenberg's work on the uncertainty in the relationship between position and momentum began in the mid-1920s when he was attempting to understand the behavior of particles within the framework of quantum mechanics. Classical physics, as developed by Isaac Newton, assumed that the world was made up of particles that followed precise, predictable paths. These particles had well-defined positions and velocities, and their future behavior could be calculated using the laws of motion. But in the quantum world, things were far more complicated. Heisenberg's uncertainty principle arose out of his attempts to make sense of the strange behavior of particles like electrons. These particles, according to quantum theory, did not behave like miniature versions of macroscopic objects. They did not have well-defined, fixed positions and velocities. Instead, they existed in a probabilistic state, meaning that their position and momentum could only be described in terms of probabilities. The more precisely we try to measure one property, the less certain we become about the other. Heisenberg first recognized this fundamental uncertainty while trying to measure the momentum of a particle using light. In classical mechanics, one could measure an object's position by shining light on it and observing its reflection. The brighter the light, the more precise the measurement would be. Similarly, to measure a particle's momentum, one would observe how it interacted with light, since light carried momentum that could be transferred to the particle. However, when Heisenberg considered this process in the context of quantum mechanics, he realized that the act of measurement itself altered the particle's state. Shining light on a particle to measure its position would impart momentum to the particle, thereby disturbing its momentum. Likewise, measuring its momentum would affect its position. This insight led Heisenberg to formulate the uncertainty principle, which is mathematically expressed as dx dp for ape, where deltax is the uncertainty in the particle's position, deltap is the uncertainty in its momentum, and h is Planck's constant, a fundamental constant in quantum mechanics. This equation tells us that the product of the uncertainties in position and momentum is always greater than or equal to a fixed value. The more precisely we measure one of these quantities, the less precisely we can know the other. This is a direct result of the wave-particle duality of quantum particles, which behave as both particles and waves. The uncertainty principle has far-reaching implications for the way we understand the behavior of particles. In the quantum world, particles do not have well-defined trajectories like classical objects. Instead, their position and momentum are spread out over a range of possible values, and their exact state can only be described probabilistically. The more accurately we try to measure one of these properties, the more the uncertainty in the other property increases. This idea challenges the classical notion that the universe operates in a deterministic way, where everything can be known if we have enough information. In classical physics, the idea was that if we had enough data about the initial state of a system, we could predict its future state with perfect accuracy. This was the foundation of Newtonian mechanics. For example, if we knew the position and velocity of a planet at one moment, we could calculate its future position using Newton's laws of motion. But in the quantum world, the situation is different. The uncertainty principle suggests that, at the quantum level, we cannot know both the position and momentum of a particle with perfect accuracy. This introduces an element of unpredictability that was previously unimaginable in classical mechanics. One of the most profound consequences of this uncertainty is that the universe at the quantum level is inherently probabilistic rather than deterministic. This means that the future behavior of a quantum system cannot be predicted with certainty, even if we know its current state. Instead, we can only predict the probabilities of various outcomes. This concept is fundamental to quantum mechanics and sets it apart from classical physics. It implies that the universe, at its most fundamental level, does not behave in a predictable, clockwork manner. Instead, it operates according to probabilistic laws, where the outcome of an event is determined by chance. The uncertainty principle also challenges our philosophical assumptions about the nature of reality. Classical physics, with its emphasis on determinism and the ability to measure everything precisely, had led to the belief that the universe was fundamentally knowable. If we had enough information, we could, in principle, understand the entire universe. However, the uncertainty principle tells us that there are limits to what we can know about the world. It suggests that there is an inherent uncertainty built into the fabric of nature, and this uncertainty is not due to imperfections in our measurement tools, but rather a fundamental feature of the quantum world. This realization has profound implications for our understanding of the nature of reality. It raises questions about the limits of human knowledge and the role of the observer in the process of measurement. In classical physics, the observer was considered separate from the system being studied. The observer could measure the properties of an object without affecting it. But in the quantum world, the act of observation itself plays a crucial role in determining the state of the system. The uncertainty principle tells us that the act of measuring a particle's position or momentum inevitably disturbs the particle, making it impossible to know both properties with perfect precision. This idea led to the development of the observer effect in quantum mechanics, which suggests that the very act of observation can influence the system being observed. The uncertainty principle also led to the development of the wave function, a mathematical description of the quantum state of a particle. The wave function describes the probability distribution of a particle's position and momentum. It is not a precise value but a range of possible values, with the probability of the particle being found in a particular location or having a particular momentum. This probabilistic nature of the wave function further emphasizes the fundamental uncertainty of quantum mechanics. The uncertainty principle has had a profound impact on the development of quantum mechanics and has shaped our understanding of the microscopic world. It laid the foundation for the theory of quantum field theory, which describes the interactions of subatomic particles and is the basis for the standard model of particle physics. The principle also underpins the development of quantum technologies, such as quantum computers, which exploit the inherent uncertainty of quantum systems to perform calculations that would be impossible for classical computers. In addition to its implications for quantum mechanics, the uncertainty principle has had a significant impact on our understanding of the nature of reality itself. It has led to a reevaluation of the role of observation in the scientific process and has forced us to confront the limits of human knowledge. The uncertainty principle tells us that the universe is not a machine that can be fully understood through measurement and calculation. Instead, it is a probabilistic system governed by uncertainty and chance. This realization has had a profound impact on both science and philosophy, as it challenges our assumptions about the nature of the world and our ability to understand it. In conclusion, the relationship between position and momentum in the quantum world is governed by Heisenberg's uncertainty principle, which tells us that it is impossible to measure both of these properties with perfect accuracy at the same time. This principle has had a profound impact on our understanding of quantum mechanics and has fundamentally changed the way we think about the universe. It has forced us to abandon the deterministic worldview of classical physics and embrace a probabilistic model of the universe. The uncertainty principle has shaped the development of quantum theory and continues to influence the way we understand the microscopic world. It is a reminder that the universe, at its most fundamental level, is not fully knowable, and that uncertainty is an intrinsic part of nature. The uncertainty principle, one of the cornerstones of quantum mechanics, revolutionized how scientists and philosophers understood the universe at the microscopic level. While it began as a concept grounded in the behavior of subatomic particles, its ramifications extended far beyond the world of physics, deeply influencing both the scientific community and the philosophical understanding of reality itself. However, as transformative as it was not immediately accepted by all. The discovery of this principle marked a turning point in the study of quantum mechanics and forced the world to abandon many of the assumptions that had defined the classical world. Heisenberg's uncertainty principle introduced an entirely new way of thinking about how we measure the physical properties of particles. Classical physics was based on the notion that objects, large or small, could be studied with precision, and any measurement could yield exact values of position, momentum, or other quantities at any given time. In classical mechanics, if you knew the position and velocity of an object, you could predict its future behavior with exactness, and it could be tracked precisely within a deterministic framework. This deterministic view, born of Newtonian mechanics, was what governed the understanding of the world for centuries. However, Heisenberg's realization, through the uncertainty principle, was that, at the quantum level, things were far more complex. The behavior of subatomic particles like electrons, which are the fundamental building blocks of matter, could not be precisely determined in the same way. When scientists attempt to measure certain properties of particles, such as their position and momentum, Heisenberg's principle showed that the more accurately one of these properties was measured, the less accurately the other could be known. This was not due to imperfections in instruments or measurement techniques, but because the universe itself at the quantum scale simply didn't work in the ways classical physics had suggested. Heisenberg's uncertainty principle introduced a fundamental shift in understanding. Rather than being a limitation of measurement, the uncertainty became an inherent characteristic of the quantum world. The principle, which is mathematically represented as deltax times deltap, is greater than or equal to h 4 pi, where deltax is the uncertainty in position, deltap is the uncertainty in momentum, and h is Planck's constant, shows that at the quantum level there is always a limit to how much information we can gather about the properties of a particle at once. This equation tells us that the more precisely we measure one property, the greater the uncertainty in the measurement of the other. This was a profound realization because it suggested that certainty and precision, so central to classical physics, were not valid at the quantum level. The uncertainty principle also deeply challenged the previously held notion that the universe was deterministic. Before Heisenberg's discovery, the classical worldview, based on Newtonian mechanics, assumed that the world followed precise, predictable laws. If the position and momentum of a particle were known, future states could be predicted with certainty. The idea that subatomic particles didn't follow these same deterministic laws was not just a challenge to physics, it was a challenge to the very way humans understood reality itself. Heisenberg's discovery opened the door to a probabilistic universe, where knowledge of a system state was no longer a guarantee of knowing its future behavior. Instead of deterministic laws governing particle motion, uncertainty and probability were now fundamental features of the physical world. Heisenberg's uncertainty principle also highlighted the nature of quantum mechanics itself. Classical mechanics, as described by Newton, relied on the assumption that particles had well-defined trajectories, but quantum mechanics introduced the idea of wave-particle duality, suggesting that particles like electrons did not have fixed positions at all times. Instead, their position could only be described in terms of probabilities, and their momentum was subject to similar uncertainty. The principle is tied to the wave nature of particles, where particles exhibit properties of both waves and particles depending on the experiment. The uncertainty principle, therefore, does not just apply to the act of measurement, it applies to the very nature of particles themselves. A particle's position and momentum are not simply values we can measure, they exist in a state of probability until we make an observation. The wave function, a fundamental concept in quantum mechanics, describes the range of possible positions and momenta a particle could have, and the act of measuring the particle collapses this wave function into a specific state. The implications of the uncertainty principle were not immediately clear to many physicists, even those working within the quantum framework. Classical mechanics had provided a clear, deterministic view of the universe for centuries, and the idea of a probabilistic universe was, to say the least, difficult to grasp. The uncertainty principle seemed to imply that the very act of measurement was an intrusion into the natural state of the universe, and the observer was no longer a passive entity in this system but an active participant that influenced the outcome. This was a difficult and unsettling idea for many in the scientific community, and it sparked a range of debates and interpretations that have lasted to this day. The philosophical implications of the uncertainty principle were just as profound as its scientific consequences. If the universe operated on the basis of uncertainty, with randomness playing a fundamental role in the behavior of particles, then many of the classical assumptions about the nature of knowledge, truth, and predictability were thrown into doubt. In classical physics, the idea that knowledge of a system's current state could lead to a perfect prediction of its future behavior was taken as a given. However, Heisenberg's uncertainty principle showed that uncertainty was not a temporary inconvenience or a flaw in measurement techniques, but a permanent feature of the quantum world. The principle suggested that knowledge of the universe was inherently incomplete. This new probabilistic framework of quantum mechanics left scientists grappling with the implications for our broader understanding of the world. If we cannot know both the position and momentum of a particle with perfect precision, then can we truly know anything about the universe with certainty? This question went beyond the realm of physics and touched on philosophical issues related to the limits of human knowledge. It suggested that the universe might be inherently unknowable in some fundamental way. It forced philosophers to reconsider ideas about the nature of knowledge and reality. Could it be that the very idea of truth as something absolute and knowable was itself a product of classical thinking, one that had to be discarded in favor of a more probabilistic view of reality? Heisenberg's uncertainty principle also led to a re-evaluation of the role of the observer in scientific experiments. Classical physics operated under the assumption that the observer could remain detached from the system they were studying. The observer was simply a passive participant in the process of measurement, gathering information without affecting the system. But in quantum mechanics, this view was no longer valid. The act of measuring a particle's position or momentum would inevitably disturb the particle's state, making it impossible to measure both properties with perfect precision. The observer was no longer a neutral party. Instead, the observer's actions influenced the outcome. This idea became known as the observer effect, and it suggested that the boundary between the observer and the system being observed was not as clear-cut as had been assumed in classical physics. While this idea was unsettling to many physicists, it opened up new avenues of thought and experimentation. It was part of a larger philosophical shift toward a more participatory and interconnected view of the universe. No longer could scientists operate under the assumption that they could study the world from a detached, objective standpoint. Instead, they had to grapple with the idea that their presence in the system influenced the outcomes of their experiments. This was a stark contrast to the classical view of science as a neutral, objective process of discovering the truth about the world. Heisenberg's uncertainty principle also had profound consequences for the development of technology, particularly in the fields of quantum mechanics and quantum computing. The principle is fundamental to understanding how quantum computers work, as these computers exploit the strange properties of quantum systems to perform calculations far more efficiently than classical computers. Quantum computers rely on the principle of superposition, where a particle can exist in multiple states at once, and on the principle of entanglement, where particles become correlated in such a way that the state of one particle is dependent on the state of another, no matter how far apart they are. These concepts, rooted in the uncertainty principle, allow quantum computers to process vast amounts of information simultaneously. In addition to quantum computing, Heisenberg's uncertainty principle also plays a key role in technologies like lasers and semiconductors, which rely on the principles of quantum mechanics to function. These technologies, which are now an integral part of our daily lives, would not be possible without Heisenberg's insight into the uncertainty that governs the quantum world. The legacy of the uncertainty principle extends far beyond the laboratory. It has inspired a rethinking of fundamental philosophical questions, including the nature of knowledge, the limits of human understanding, and the role of the observer in the process of scientific inquiry. In the context of physics, it helped pave the way for quantum mechanics, a theory that continues to shape our understanding of the universe and our place within it. The uncertainty principle reminds us that the universe is not a deterministic machine, but a probabilistic system that operates according to the laws of chance and uncertainty. While this realization may be unsettling, it has also opened up new avenues of thought, discovery, and technological advancement. It has shown us that uncertainty, far from being a flaw, is a fundamental and essential feature of the natural world. As we continue to explore the profound implications of Heisenberg's uncertainty principle and its groundbreaking influence on quantum mechanics, we turn our attention to one of the most significant aspects of this theory, how it reshaped our understanding of the deterministic nature of the universe. Prior to the advent of quantum mechanics, and particularly Heisenberg's uncertainty principle, science operated under the assumption that the universe was a predictable machine governed by deterministic laws. This view was deeply entrenched in classical physics and was encapsulated by the works of Isaac Newton and other early physicists. According to this worldview, if you could measure the position and velocity of an object with precision, you could predict its future motion with complete certainty. The deterministic model of the universe was a comforting idea. It suggested that, given enough information, we could understand everything and predict the future with absolute precision. Classical physics governed the behavior of everything from the motion of planets to the trajectories of baseballs. The laws of motion formulated by Newton were considered universal truths that applied to all objects, from the largest celestial bodies to the smallest particles. However, Heisenberg's uncertainty principle shattered this comforting picture by introducing an element of indeterminacy into the world of physics. The uncertainty principle states that the more precisely we measure certain properties of a particle, such as its position, the less precisely we can know its momentum, and vice versa. This inherent uncertainty is not a result of any flaws in our measurement tools, but a fundamental property of nature itself. At the quantum level, The universe does not behave like a mechanical clockwork system with precise, deterministic rules. Instead, it operates according to probabilistic laws, where outcomes are not strictly determined by prior states but are instead described by probabilities. This shift from a deterministic worldview to a probabilistic one was nothing short of revolutionary. It marked a profound change in how scientists viewed the nature of reality. The implications of this shift were far-reaching, not just for physics, but for philosophy and the way we think about the universe and our place within it. The deterministic model that had guided classical physics for centuries was replaced with a probabilistic framework in which uncertainty and randomness were fundamental features of the universe. The most profound consequence of Heisenberg's uncertainty principle was the recognition that the universe at the quantum level does not adhere to the same rules as the macroscopic world we experience. In the classical world, if we knew the position and momentum of a baseball, for instance, we could predict where it would go next. In quantum mechanics, however, particles such as electrons do not have well-defined positions and momenta. Instead, they exist in a state of probability, with their position and momentum described by wave functions rather than exact values. The uncertainty principle revealed that the act of measuring one property, such as position, necessarily disturbs the other property, such as momentum, in an unpredictable way. This introduced a level of fundamental uncertainty that is impossible to overcome, no matter how advanced our measurement tools may become. In essence, the uncertainty principle asserts that the very concept of exact knowledge is not applicable at the quantum level. When we attempt to measure the properties of a particle, we are not uncovering an objective reality, but rather interacting with the system in such a way that the act of measurement alters the system itself. This is a departure from classical physics, where the observer was considered a passive participant in the measurement process. In the quantum world, the observer plays an active role in determining the outcome of an experiment. This idea had significant philosophical ramifications. Classical physics had promoted a mechanistic view of the universe, where everything could, in theory, be predicted and understood with enough information, but the uncertainty principle shattered that belief. The universe, at its most fundamental level, was no longer a predictable machine. It was probabilistic and uncertain. This raised deep philosophical questions about the nature of reality and the limits of human knowledge. If we cannot know the position and momentum of a particle with perfect precision, then how can we know anything with certainty? The uncertainty principle forced us to confront the limits of our understanding and accept that the universe, at the quantum level, is inherently unknowable in certain ways. Moreover, the uncertainty principle also had profound implications for the concept of causality. In classical physics, the idea of causality was central to our understanding of the universe. If we knew the initial conditions of a system, we could predict its future behavior with certainty. This was the essence of determinism. Given the right set of conditions, the future was an inevitable consequence of the past. However, in the quantum world, this idea of strict causality was replaced by probability. The uncertainty principle showed that events at the quantum level do not have definite causes in the way classical physics assumed. Instead, outcomes are probabilistic, and we can only predict the likelihood of a given result, not the exact outcome. As revolutionary as Heisenberg's uncertainty principle was for the understanding of the quantum world, it also challenged the very notion of reality itself. For centuries, the scientific community had embraced a view of the world in which objects and their properties existed independently of our observation of them. The world was considered to have a definite state, and our task as scientists was to uncover this state through measurement and observation. However, the uncertainty principle introduced a new perspective. In the quantum world, the act of observation is intimately connected with the state of the system being observed. This challenged the classical view of reality as something independent of the observer. Instead, Heisenberg's principle suggested that the very nature of reality was intertwined with the observer's interaction with it. This shift had far-reaching implications not only for physics but for the philosophy of science. If the observer plays an active role in determining the state of a system, then how can we claim to have objective knowledge of the world? Can we ever truly know anything about the universe, or are we always limited by our inability to measure everything with perfect precision? These are deep questions that continue to be explored by philosophers, physicists, and other scholars. Heisenberg's uncertainty principle forced a re-evaluation of our assumptions about knowledge, truth, and reality. Furthermore, Heisenberg's principle opened up new avenues of research in quantum mechanics and led to the development of new technologies. The understanding that particles behave probabilistically rather than deterministically was crucial in the development of technologies such as semiconductors, lasers, and quantum computers. These technologies, which have transformed industries ranging from telecommunications to computing, would not have been possible without the fundamental insights provided by Heisenberg and his contemporaries. In the realm of quantum computing, for example, Heisenberg's uncertainty principle plays a pivotal role in the development of algorithms that exploit quantum superposition and entanglement. These properties of quantum systems allow quantum computers to perform complex calculations at speeds far beyond the capabilities of classical computers. Quantum computers are able to process vast amounts of information simultaneously by leveraging the uncertainty and probabilistic nature of quantum particles. Without the uncertainty principle, the entire framework of quantum mechanics, and by extension, quantum computing would not exist. The principle also laid the groundwork for the development of quantum cryptography, a field that uses the principles of quantum mechanics to create secure communication systems. Quantum cryptography takes advantage of the fact that quantum states cannot be copied or measured without disturbing them. This allows for the creation of communication systems that are theoretically immune to eavesdropping, as any attempt to intercept a quantum transmission would alter its state and be detected. In addition to its technological applications, the uncertainty principle continues to shape our understanding of the natural world. It has led to the development of quantum field theory, which describes the behavior of subatomic particles and their interactions through the exchange of force-carrying particles. This theory forms the foundation for the standard model of particle physics, which is the most successful theory we have for describing the fundamental forces and particles that make up the universe. In conclusion, the Heisenberg Uncertainty Principle revolutionized not only the field of physics but also our understanding of the universe and our place within it. By introducing the concept of inherent uncertainty at the quantum level, Heisenberg challenged the deterministic view that had dominated classical physics for centuries. This shift to a probabilistic framework has profound implications for both the philosophy of science and the development of technology. It has reshaped our understanding of causality, measurement, and reality itself, forcing us to reconsider what it means to know the universe. While the uncertainty principle introduced uncertainty into our knowledge of the world, it also opened up new avenues of thought, discovery, and technological advancement. It remains one of the most important and far-reaching discoveries in the history of science. Heisenberg's discovery of the uncertainty principle not only revolutionized quantum mechanics, but also fundamentally challenged long-standing assumptions about how the universe operates at the most basic level. Prior to Heisenberg's work, the prevailing belief in science was rooted in the deterministic view of classical physics, where the position and momentum of particles could be known simultaneously with perfect accuracy. In this classical framework, if the state of a system at one point in time was known, its future state could be predicted with complete certainty. However, Heisenberg's uncertainty principle introduced a radical shift in how we understand measurement and the limits of our knowledge, particularly in the quantum world. The principle asserts that it is impossible to measure both the position and momentum of a particle with absolute precision at the same time. This inherent limitation is not a flaw in our instruments, but a fundamental characteristic of nature itself. This discovery was revolutionary, as it challenged the previously held notion that the universe could be fully understood and predicted with precision. The implications of this principle were far-reaching. It meant that, at the quantum level, the universe could not be completely understood through classical measurement methods. Heisenberg's insight led to a profound shift in how scientists began to view the behavior of subatomic particles. Particles like electrons were no longer treated as objects with fixed positions and velocities, but instead were seen as existing in a probabilistic state. Instead of precise measurements, their properties were described in terms of probabilities. This led to a new understanding of the behavior of particles, where instead of knowing an exact location and momentum, scientists could only calculate the likelihood of where a particle might be found and its momentum at any given time. The uncertainty principle also brought about a deeper philosophical change. It questioned the idea that reality exists independently of observation. In classical physics, the observer was seen as separate from the system being studied, and measurement was viewed as a passive process. However, the uncertainty principle suggested that the very act of measuring a quantum system alters its state, meaning the observer has an active role in determining the outcome. This philosophical shift introduced the idea that the act of observation is inherently linked to the state of the system itself. This became a key feature of the observer effect in quantum mechanics, where the observer influences the system in a way that makes it impossible to fully separate the two. As scientists began to embrace the probabilistic nature of quantum mechanics, the uncertainty principle also laid the groundwork for technological advancements. For example, the principles of quantum mechanics, underpinned by Heisenberg's work, led to the development of quantum computers. Quantum computers exploit the uncertainty of quantum particles, allowing them to process vast amounts of information simultaneously, offering potential far beyond classical computing. Quantum cryptography, which relies on the same principles, has also provided a way to create virtually unbreakable encryption systems, taking advantage of the fact that quantum information cannot be copied or intercepted without disturbing the system. These developments show how Heisenberg's uncertainty principle, initially a philosophical and theoretical breakthrough, directly influenced real-world technologies that are now an integral part of modern life. The uncertainty principle also played a central role in shaping the direction of further research in quantum mechanics, influencing subsequent theories and experiments. It underscored the necessity of embracing uncertainty as a fundamental property of the quantum world. This approach led to the development of quantum field theory, which describes how particles interact and exchange forces. Quantum field theory, one of the most successful theories in physics, helps explain the behavior of fundamental particles and their interactions, providing the theoretical foundation for the standard model of particle physics. Thus, Heisenberg's principle not only altered the course of quantum mechanics but also paved the way for ongoing discoveries in particle physics, changing our understanding of the universe on both the smallest and largest scales. Heisenberg's uncertainty principle stands as one of the most pivotal discoveries in the history of science, reshaping the entire landscape of physics and our understanding of the fundamental workings of the universe. Prior to Heisenberg's groundbreaking work, the scientific community adhered to the classical view of physics, which was grounded in the belief that the universe was entirely deterministic. This perspective, drawn from the principles of Newtonian mechanics, suggested that if we knew the precise position and momentum of an object at any given time, we could predict its future trajectory with absolute certainty. The classical model assumed that the universe operated like a well-oiled machine, governed by clear-cut, predictable laws. However, the introduction of the uncertainty principle shattered this understanding, revealing that the very nature of reality at the quantum level was far more complicated and uncertain than classical physics had ever imagined. The uncertainty principle asserts that it is impossible to simultaneously know both the exact position and momentum of a particle with perfect precision. This was a revolutionary concept because, in classical physics, the idea of precise measurements and predictions was considered the foundation of all scientific inquiry. Heisenberg's realization that measurement itself introduces a level of uncertainty where measuring one property of a particle more accurately makes the other property less certain, forced scientists to abandon the notion of a deterministic universe. This new principle of uncertainty applied not just to measurements, but to the nature of subatomic particles themselves. Instead of particles having fixed, well-defined positions and velocities, the uncertainty principle suggested that they existed in a state of probability where their true properties were spread across a range of potential values. The exact state of a particle could not be known until it was measured, and even then, the measurement itself altered the particle's state. Heisenberg's discovery also brought forth the realization that the very act of observing or measuring a quantum system changed the system. This introduced a new relationship between the observer and the observed, where the observer was no longer a passive participant in the measurement process. The uncertainty principle suggested that the presence of an observer could affect the outcome of an experiment, a concept that was alien to classical physics, where the observer was expected to remain detached and unaffected by the system being studied. This active role of the observer in quantum mechanics became a cornerstone of the observer effect, which has since become one of the most debated aspects of quantum theory. The observer effect suggested that reality, at the quantum level, was not fixed and could not be separated from the act of measurement, fundamentally changing our conception of objectivity and reality. The uncertainty principle's implications extended beyond theoretical physics into technology and practical applications, especially in the field of quantum computing. Quantum computers, which harness the principles of quantum mechanics, including the uncertainty principle, have the potential to perform complex calculations far more efficiently than classical computers. Quantum computers exploit quantum superposition and entanglement, two phenomena that arise from the probabilistic nature of quantum particles. The principle of superposition allows quantum computers to handle multiple states simultaneously, dramatically increasing computational power. This leap in computational capability opens up possibilities for solving problems that would otherwise be intractable for traditional computers, such as simulating molecular structures or solving optimization problems. The uncertainty principle, which initially seemed to undermine classical ideas of precision, has thus paved the way for a new era of technological innovation. Moreover, Heisenberg's principle played a central role in the development of quantum cryptography. This emerging field of technology uses the inherent uncertainty of quantum systems to create secure communication channels. The principle that observing or measuring a quantum system changes its state is a powerful tool for securing information. In quantum cryptography, any attempt to eavesdrop on a communication would disturb the system and be detected, making it virtually impossible for a third party to intercept or tamper with the information. This reliance on quantum mechanics, and specifically the uncertainty principle, has made quantum cryptography one of the most promising fields for secure communications in an increasingly digital world. The principle's real-world applications are a testament to how foundational scientific discoveries can ripple outward to shape the future in unexpected ways. In conclusion, Heisenberg's uncertainty principle not only transformed our understanding of quantum mechanics, but also altered the way we think about the universe itself. It challenged the deterministic framework that had dominated classical physics, ushering in a new, probabilistic view of nature. The principle not only deepened the philosophical questions about the nature of reality and observation, but also laid the groundwork for revolutionary advancements in technology. Quantum computing and cryptography, both made possible by the principles Heisenberg uncovered, are changing industries and will continue to shape the future of science and technology. The uncertainty principle reminds us that uncertainty is not merely a limitation of measurement or knowledge, but a fundamental feature of the universe itself, shaping our understanding of the world at its most fundamental level. Heisenberg's uncertainty principle is one of the most profound and transformative discoveries in the history of modern physics, fundamentally changing our understanding of the universe. Before Heisenberg's groundbreaking work, science operated largely within the deterministic framework of classical mechanics, as put forward by Isaac Newton. According to classical physics, the universe could be understood as a vast, intricate machine that operated according to predictable, fixed laws. If we could measure the position and momentum of any object with sufficient precision, we could predict its future state without error. This view of the universe as a deterministic system of predictable motions prevailed for centuries and had deep philosophical roots, implying that everything in the universe could be ultimately understood if one had enough information. However, Heisenberg's discovery shattered this notion, showing that nature at the quantum level did not work according to these predictable laws. The uncertainty principle asserts that there is a fundamental limit to how precisely we can measure certain pairs of physical properties of a particle, such as its position and momentum. Heisenberg's breakthrough was not just a theoretical consideration. It was based on the observation that the very act of measurement at the quantum scale influences the state of the system. In other words, the process of measuring one property, such as the position of a particle, disturbs the other property, such as its momentum, making it impossible to know both with complete precision simultaneously. This idea was radically different from the classical physics model, where such measurements could be made with arbitrarily high accuracy. The uncertainty principle showed that, at the quantum level, uncertainty was an intrinsic feature of nature, not a flaw of measurement or instruments. This discovery forced scientists to abandon the classical view of particles as objects with fixed, well-defined properties. Instead, quantum mechanics, underpinned by the uncertainty principle, introduced the concept of probabilities. Rather than being able to predict the exact position or momentum of a particle, scientists could only describe the likelihood of where the particle might be or what its momentum could be. This probabilistic nature of quantum mechanics led to a deeper understanding that the universe at the quantum level is fundamentally different from the macroscopic world we experience. At larger scales, the laws of classical physics still hold true, and we can accurately measure the position and momentum of objects. However, at the microscopic scale of atoms and subatomic particles, uncertainty becomes a fundamental characteristic guiding the behavior of the system. The uncertainty principle also had profound philosophical implications, particularly concerning the nature of reality and knowledge. In classical physics, the observer was considered a passive participant in the measurement process, meaning the system being measured existed independently of the observer. However, Heisenberg's discovery revealed that the act of measurement itself affected the system. This led to the idea that the observer plays an active role in shaping the outcome of the experiment. This concept introduced the observer effect, which suggested that the boundary between the observer and the system being observed was not as clear-cut as had been assumed in classical physics. The implication was that reality at the quantum level cannot be fully separated from the observer, challenging the objectivity that classical science had long embraced. One of the most revolutionary aspects of Heisenberg's uncertainty principle was its challenge to the deterministic view of the universe. Classical physics was rooted in the belief that if we knew the state of a system at a particular time, we could predict its future with perfect accuracy. This deterministic worldview allowed for the belief that everything, from the motion of planets to the fall of an apple from a tree, could be predicted if the initial conditions were known. However, the uncertainty principle introduced a probabilistic framework in which future events could not be predicted with certainty. This shift to a probabilistic model was difficult for many scientists to accept, as it upended the long-held belief that the universe followed a set of predictable, deterministic laws. Instead, the future of a quantum system could only be described in terms of probabilities, with various outcomes having a certain likelihood of occurring. Despite the challenges it posed to classical physics, the uncertainty principle laid the foundation for the development of quantum mechanics, which has since become the dominant theory for understanding the behavior of particles at the smallest scales. Quantum mechanics, fueled by Heisenberg's principle, has led to groundbreaking discoveries in fields like particle physics, quantum field theory, and quantum computing. The development of quantum technologies such as semiconductors, lasers, and even quantum computers is based on the probabilistic behavior of particles as described by the uncertainty principle. These technologies are now integral to our daily lives, from the devices we use to communicate, to advances in medical imaging, to cutting-edge research in artificial intelligence and quantum information systems. In conclusion, Heisenberg's uncertainty principle was a transformative discovery that not only changed the trajectory of physics, but also reshaped how we view the universe itself. The principle forced a shift from a deterministic to a probabilistic view of nature, introduced new ways of thinking about the role of the observer in science, and laid the groundwork for revolutionary technological advancements. It also provided a deeper, more nuanced understanding of reality, one that continues to shape both scientific inquiry and philosophical debates to this day. The uncertainty principle remains one of the most influential and far-reaching ideas in the history of science. Its impact felt in both the theoretical realm and in practical applications that have changed the world. Werner Heisenberg's uncertainty principle remains one of the most profound discoveries in the history of physics, shifting the very foundations of our understanding of the natural world. Before Heisenberg's work, classical physics, rooted in the principles of Isaac Newton, held sway. This deterministic view of the universe asserted that, given enough information about the position and velocity of an object, one could predict its future behavior with absolute certainty. Classical mechanics painted a picture of a universe that functioned like a clockwork machine, operating according to fixed laws of motion. However, Heisenberg's uncertainty principle shattered this classical perspective by introducing a radical new way of thinking about measurement, knowledge, and the nature of reality itself. The uncertainty principle asserts that there is a fundamental limit to how precisely certain pairs of physical properties of a particle, such as its position and momentum, can be known simultaneously. This limitation is not due to imperfections in measurement tools or errors in technique, but is an inherent feature of the quantum world. The principle tells us that the more precisely we try to measure one property of a particle, the less precisely we can know the other. This insight was groundbreaking because it directly contradicted the classical belief that all physical properties could be measured with arbitrary precision. It suggested that at the quantum level, the universe could not be understood through simple measurement alone. This revelation had profound consequences not just for physics but for our understanding of the very nature of the universe. It meant that the classical, deterministic worldview was no longer adequate to describe the behavior of subatomic particles. Instead of treating particles as small, predictable objects with fixed positions and velocities, quantum mechanics proposed a new framework where particles existed in a state of probability. Their position and momentum were not fixed but existed as a range of possible values described by wave functions. When we measured a particle, the act of measurement itself caused the wave function to collapse, giving us a specific value, but the exact state of the particle before measurement could only be known probabilistically. Heisenberg's uncertainty principle also introduced a radical new perspective on the role of the observer in science. Classical physics had assumed that the observer could remain detached and objective, measuring the properties of a system without influencing the system itself. However, in quantum mechanics, the uncertainty principle suggested that the act of measurement could not be divorced from the system being studied. When we measure a quantum system, the observer inevitably influences the system's state. This became known as the observer effect, which challenged the very idea that reality could exist independently of our observations of it. This notion was revolutionary because it blurred the line between the subjectivity of the observer and the objectivity of the system being studied. In addition to altering the understanding of measurement and observation, the uncertainty principle also had profound philosophical implications. It raised fundamental questions about the limits of human knowledge. If we cannot measure the position and momentum of a particle simultaneously with perfect precision, how can we claim to know anything with certainty? This uncertainty, at the quantum level, suggested that the universe may not be fully knowable in the way we had previously believed. It introduced the idea that, no matter how much we learn, there will always be aspects of reality that are fundamentally out of reach, governed by probability and indeterminacy. While Heisenberg's uncertainty principle was initially met with skepticism, its implications were eventually confirmed by experiments and became one of the cornerstones of quantum mechanics. The principle helped to explain phenomena that classical physics could not, such as the behavior of electrons within atoms. It also contributed to the development of quantum field theory, which describes the interactions between subatomic particles and is the basis for the standard model of particle physics. The uncertainty principle helped to establish quantum mechanics as the dominant framework for understanding the behavior of matter at the smallest scales. The practical implications of the uncertainty principle extended beyond theoretical physics into the realm of technology. Quantum mechanics, underpinned by Heisenberg's insights, has led to numerous technological advancements. For instance, technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI, rely on principles of quantum mechanics. Perhaps the most striking example of quantum mechanics' influence is the development of quantum computers. Quantum computers take advantage of the inherent uncertainty and probabilistic nature of quantum particles to perform complex calculations much faster than classical computers. These advancements have the potential to revolutionize fields ranging from cryptography to medicine, showcasing the far-reaching impact of Heisenberg's work. In summary, Heisenberg's uncertainty principle transformed the landscape of science by introducing a fundamental uncertainty at the heart of the quantum world. It challenged the deterministic view of the universe, revolutionized our understanding of measurement, and forced us to reconsider the role of the observer in science. This shift in perspective laid the groundwork for the development of quantum mechanics and continues to influence technological advancements to this day. The uncertainty principle reminds us that the universe at the smallest scales operates not with certainty, but with probability, forcing us to acknowledge the limits of our knowledge and the probabilistic nature of reality itself.